Now let's look at how to design a decoder. Basically, you just follow the same steps as we talked in lecture 7 for combinational circuit design. So the first step is to understand the project. But here it's very clear. We want a 3 to 8 decoder. And step 2, get the truth table. We already have the truth table. So we can directly move to step 3. Basically to find the Boolean expression for each output. So we have 8 output here, so we need one expression for each one. So for D0, and because we only have one case that the output is 1, so we don't even need the column map. We can directly write D0 should equal to when x is 0, y is 0, and I is 0, z is 0. D1 equal to x0, y0, z equal to 1. D2 equal to x0, y, z equal to 0. And D3 equal to x0, y, and z. D4 equal to x, y0, z0. D5 x, y0, z. D6 x, y, z prime. D7 x, y, z. Okay, then we just draw the logic diagram for all this output. Then we get the decoder circuit using logic gates. Pretty simple, huh? But there is one more thing we can get from this slide, is that we know that each output corresponding to a mini terms here, right? Applications. The first application where we use decoder is that we can use it to implementing some logic functions. For example, if say we wanted to realize a Boolean function that equal to this, what we can do? So from previous slides, we learned that the output of the decoder can be represented using a miniterm, right? So if we can have this function written in minterm, then we can do it. So how to expand this to minterm? The first two terms are already minterms. For the last term, actually what we do is to add this. Because we know a or a prime equal to 1, right? And the 1 by bc still equal to bc. So this won't change anything. Then we got a b prime c prime, or a b c prime, or a b c, or a prime bc. Actually, we can even write this into the minterm list form, which equal to, this is 1 0 0, this is 4 1 1 0, 6 1 1 1, so we got 4 6 7 0 1 1 3, so we got 3 4 6 7 here. So what we need to do is basically find y3, y4, y6, and y7, and collect them together using an OR gate. That's how simple it is. Because y3 corresponding to the minterm a prime bc, y4 corresponding to a b prime c prime, y6 corresponding to a b c prime, y7 a b c. Right? You can check with the previous slide to see if I'm right. And if the function changes, you can still manipulate with the output and OR gate to realize it. The second common application for decoders is in the memory, in the computer memories. and we call this address decoding. This is a very commonly used technique for accessing memory data. Okay, yes, where we can see this is kind of in the RAM. This is a memory card for a computer, and on the right is a logic diagram to show you how the decoder is used in that system. Say we have 8 memory chips here. Every chip is the same. They are 8K by 8 EPROM. EP means erasable and programmable read-only memory. Okay, so there are fixed data stored in those memories, and many times, like always, we need to read data from these memory chips. But how to accurately find the right data to read? That's the problem here. Okay, because we have so many chips, and in each chip we have 8K different locations, and in each location we can store 8-bit data. That's what the 8K by 8 means. So 8K means 8,000 different locations, and each location there store the 8-bit data. And we have 8 chips here. Just name them 1, 0 through 7. Okay. So totally we have 64K different locations. In order to find the specific location to read the data, we need the address bus. In this case, because we have 64K different location, we have we need 20-bit address bus here, and specifically the bit A19 through 16 is used to drive this decoder, 3 to 8 decoder, and the bit A15 to 13 are used to select the right chip. Okay. Between these 3 bits will tell you which chip to use, 0 to 7. Pick one of them. So this is the decoder. Depending on the value here, we can select the one we want. And the address bus A16 A12 to 0 is used to find the locations in the selected memory chip. That's how it works. So basically we can use the example to talk about this. Say I want to reach the location. So I got 8K. Let's try the location 100 in chip 5. Now how do we configure the address bus? First, A19 to 16 is used to enable the decoder, so their value will be fixed. It has to be 1. Right? Remember we talked about this decoder? And since we are going to select chip 5, 1, 2, 3, 4, 5, so this chip here, the A, B, C, so C here is the MSB, so CBA corresponding to A15, 14, 13, they should equal to 1, 0, 1. So this will select the 5th output here, and it's active no output, so it will this line will give a 0 out here, and this 0 will pass in through this OR gate. And by the way, before we read it, before we do the read operation, we need to set this read enable to 0. You see it has a bar there, means 0. We activate the read operation. Actually, this read line is connected to the other input of the OR gate. So we have 0, 0, we will get a 0 here. This 0 will can activate this memory chip, because this CS is the enable input for this chip, and it's active now. So 0 will enable this. Sorry, that's the wrong chip, right? This one here. Okay. Then A12 to 0 will tell you where the data is located. So we want the location is 100. So we need to convert 100 to 12-bit binary. Okay, how to do that? 100 equal to 64 plus 32, that's 96 plus 4. So we write as 1, 1, 30, 16, 8, 4. Okay, that's 100 in 7-bit. So we need to add 50 before it to make it 12-bit. So we need to fill 0, 0, 0, 0, 0, 1, 1, 0, 0, 1. Actually, sorry, 13-bit, because it's 12 to 0. So I missed 1 0 here. 1, 1, 0, 0, 1, 0, 0. Okay, so if we send this long code to the address bus, then we can find the data stored in this location. The last commonly used application for decoder I want to introduce here is that to drive the 7-segment display, LCD display. Okay, this type of display is commonly seen in a calculator or on the PCB board. And we will use a special decoder to do this job. This decoder is called BCD to 7-segment display. Basically, for this decoder, we have 4 input, but we only have 7 data output. Okay, there are some enable input there, but yeah, you know, you can check the datasheet to see how they works. But basically, we just talk about the relation between the input and output here, and how we can use it to drive the 7-segment LED display. Okay, and a little about the display. It's called 7-segment because it's composed of 7 LEDs, starting from here. So A, B, C, D, E, F, G. So 7 small pieces of LED there, and most cases this LED are active now. So which means at 0 we'll turn them on, and 1 will turn it off. Okay. So for this decoder, we will use this decoder to manipulate which output to be 0, so we can turn to be 0 or 1, so we can turn on and off the corresponding LED. Okay, so a big difference between this decoder and the regular decoder we talked before is that for this decoder, multiple output can be active at the same time. So it's not a big issue because we can totally design things like that. The most important thing is just to figure out the truth table. No, we can realize this circuit using logic gates with no problem. So let's see how this works. So for this 7-segment display, if we want to display the digits from 0 to 9, and here shows which LED should be on in each case. So we can figure out the truth table based on this. For example, if the input for the decoder is 0, 0, 0, 0, basically we want the display to show 0. Okay, but to show 0, which means the LED A, B, C, D, E, F should be on, G should be off, right? And because all the LEDs are active now, so which means we have 0, 0, 0, 0, 0, 0, 1 here. Okay, and for input 0, 0, 0, 1, we want to display 1, which means only B, C is on. So we got a 1 here. 0, 1, 1, 1. Okay. The next, to display 2, only C and F is off. So F is off, C is off, all others should be on. For number 3, only E and F is off. The others will be on. For 4, A should be off, B on, C on, D, E off, F should be on, G should be on. Okay. For 5, B and E off. So B should be off, E should be off. For 6, only B is off. For 7, ABC is on. For 8, everything is on. For 9, only E is off. Okay, so but after 9, those states are not used here. So you can just put X for them because they are unused states, like they never will showing at the input. We will try to avoid that. But if we don't, but in many cases actually we don't have to put them to don't care. Actually, in most cases they display. We want to use it to display the hexadecimal number. So basically we have another 6 number here, which is A, B, C, D, E, F. However, because like B, if we display the big B, it will be same as 8. So we use small b instead. Similarly, the big D would be same as 0. So we use small d. Okay. Then let's see what will happen. For A, it looks like that. So only D will be off. So we have A, B, C, D, F, G. For B, it's small b. It will look like that. So AB is off. To display C, B, C, G is off. Right? And for small d, basically A and F is off. So 1, 0. And for E, BC is off. And for F, BCD is off. So we can expand this truth table to like hexadecimal display. Yeah. And all you have to do is figure out the Boolean expression for A, B, C, D, F, G respectively and design a circuit. That's all I want to talk about decoders. Hope you enjoy this video too. Yeah, if you like it, please help share and subscribe. I will see you next time.